Today we'll be looking at large sample run test, which is a non-parametric statistics. Run test is one of the non-parametric statistics to take decision. We can either have the small sample run test and we also have a large sample run test, but for this video we'll be looking at large sample run test. First of all, run test can be used to decide if a data set is from a random process. It is a test for randomness, in short. All statistical tests require random sample, so this test may be used to check that a sample has been randomly collected. Alright, so we'll go deep into this now. So the sampling distribution of R is approximately normal with a mean and standard deviation of, we have the normal, standard normal equals to R minus mu subscript R divided by sigma subscript R, whereby this is the symbol for our standard normal. Then we have R, which is for the sampling distribution approximately for normal. Then we have a mean of R, that is mean that has to do with this run test. Then we have the standard deviation for the run test. So now we need to split this. How do we get this mean? So we have mu subscript R, this is given us. The mean is given us mu subscript R equals to 2n1 n2 divided by n1 plus n2 plus 1. Now, the n subscript 1 is the observation of the first symbol, while n2 is the observation of the second symbol. Now, n1 plus n2 is the total observation of all the symbol. For example, now we are looking at defective of a material, whether a material is defective or non-defective. So we can say n1 should be the total number of defective products, while n2 should be the total number of non-defective products. So by the time we add n1 and n2 together, we're going to have the total product. Now we also need to know this standard deviation of the run test. So how do we get that? We say why the standard deviation is given us mu subscript R equals to 2n1 n2 into bracket 2n1 n2 minus n1 minus n2 divided by n1 plus n2 raised to the power 2 into bracket n1 plus n2 minus 1. So now this is the standard normal approximately for this run test. Now the mu R, which is the mean for the run test, this is the formula to get that. And the standard deviation for the run test, this is the formula to get it. Now, why do we say this is a large sample runs test? The reason is that if n1, any of the n1 and n2 is greater than 20, if any of the n1 or n2 is greater than 20, let's say n subscript 1 is greater than 20, or we have it as n subscript 2 greater than 20. So if any of the n is greater than 20, then we said it is a large sample runs test. Large sample runs test. Alright. So now we go further by showing us how to calculate that with this formula. So we're going to look at one example now. It's test the following sequence of observation by using the run test and alpha to be equals to 0.05 to determine whether the process produce random results of this symbol here. We have MMMMM and N, MM, NN, MMM, N, and such up to this point. So now the target here now is that we have the level of significance to be alpha, which is equals to 0.05. And what are we testing? We are testing run test here. We are testing run test here. So now, is this small sample run test or large sample run test? So we're going to know now if any of the symbol is greater than 20. We can just assume that we are dealing with production of a product on the machine. Then M should stand for a number of defective, and N should stand for number of products that are not defective. We can just look it that way. Now it's a solution. Then how do we stand now? First of all, we need the number of run. And how do we get the number of run? That is R from the formula. So we say, what is the number of stand that we have here? You see, we have MMM, we have NN, we have MMM, we have NN, MMM, N. So now up to this MMM here. So by the time we count the number of stand here, so we have 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So now we have 15 number of run here, so it means our R equals to 15. So for N1, which is should represent M, and M stand for number of defective. So how many M do we have here? I'll make it easier by coloring M so that it will be easier for us to count. So if you count all this M here, you count all this M, all this M, all this M, 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 M. At the end, we are going to count 34. And by the time you count the number of N, the number of N, the number of N, the number of N, all the N that we have here is a 16. So we have R to be equals to 15, N1 is 34, and N2 is 16. The number of runs, 1, 2, you count the number of stand, the number of run here, and that total to be 15. Now N1, which is the number of defective, which is M, if you count the number of M in all these are randomness, either it is random or not random, in this product, we notice that we have a 34 and the number of N equals 16. So now we are going to take this step by step. Now, step 1 is to know the hypothesis. What is the hypothesis? So we are going to state the null hypothesis against the alternative hypothesis. So we say the observation in the sample were generated randomly. That is the null hypothesis. That this observation, all these observations here and the sample were generated randomly against the alternative hypothesis, which is the opposite of the null. That is, the observation in the sample were not generated randomly. So that is the first step, which we've stated the hypothesis. Now the second step now is to know the level of significance. We say, and our level of significance from the question is alpha equals 0.05. That is the level of significance. Now this is the second step to this. Now the third step is to use the statistical test. Let's assume that we don't even know that we are running we have to use a run test. So we have to choose the appropriate statistical test in order to know what we are doing. So it says step 3, statistical test. And what are we testing here? We're testing the large sample runs test. We should not forget that from our previous slide, we have the number of N1. We have the number of N1 to be equals to 34. This alone has already shown us that we have to use the large sample runs test. Why? Because this N is greater than 20. If it is less than 20, if N1, N2 has a value that is less than 20, then that is a small sample runs test. Now, in the fact that we have one of the N which is greater than 20, so we have to use a large sample runs test. So, all right, and this test is given as normal standard equals to R minus mu subscript R divided by sigma subscript R. this is our standard normal, which is approximated for the run test, and we have R to be the number of run, we have the mean mu R for the runs, and we have the standard deviation for the runs. Now the first thing we need to do is to remind us the formula for calculating this mu subscript R, which is the mean. Then we said mu subscript R equals to 2n1 n2 divided by n1 plus n2 or plus 1. I've given us this formula in the first slide, but we have to remind ourselves here. So we say 2n subscript 1, n subscript 2 divided by n subscript 1 plus n subscript 2 plus 1. We have to take note of this formula very well, and we should not make any mistake. And we should not forget that our n1 equals to 34, and our n2 equals 16. So we have our n2 to be equals to 16. So that is what we are going to be looking at now. So we say mu subscript R equals to 2 into bracket 34 into bracket 16 divided by 34 plus 16 plus 1. If we substitute n1, n2 into this formula, we're going to have this. So by the time we multiply 2 times 34 times 16 divided by 34 plus 16, this will definitely give us 21.76. Then we have this plus 1, of course. So we have 21.76. So by the time we add everything together, we're going to have a 22.76. So we should take note of this value of the mean, because we are going to use it in the man formula. So we have a 22.76 as a mean for the run. Alright, so we'll move forward. We need to get our standard deviation. Standard deviation here, which is a sigma subscript R. So we said sigma subscript R equals square root of 2n1 n2 into bracket 2n1 n2 minus n1 minus n2 all divided by n1 plus n2 raised to the power 2, n1 plus n2 minus 1. So this is the formula for calculating the standard deviation. We should take note of this formula so that we will not make mistake. You can see this is a combination of n1 and n2. So now we should remember that our n1 still remains 34 and our n2 remains 16. If we substitute n1 and n2 into this all formula here, we're going to have a 2 into bracket 34 plus multiply by 16 into 2 into bracket 34 multiply by 16 minus 34 minus 16 divided by 34 plus 16 raised to the power 2 to bracket 34 plus 16 minus 1. So this sign here means multiplication. This is 34 multiplied by 16. This is 34 multiplied by 16. And all this is we just substitute the value into this formula and we come up with this. So what do we do now? If we multiply 2 times 34 multiplied by 36, we're going to multiply the whole of this. We're going to add this and square it. Then if you do this and square it, and definitely we're going to have the square root of 1088 multiplied by 1038 divided by 50 squared multiplied by 49, and that will give us 1129344 divided by 122500, which means if we simplify this, we multiply 1088 multiplied by 1038, we're gonna have this 50 squared multiplied by 49 will definitely give us this. Now by the time we now divide this value here and square it, so we're going to have a square root of 9.2191, and that will give us 3.0363 by the time we find the square root. So now again, our standard deviation is 3.0363. we also need that. So the value of the mean for the run and the standard deviation for the run, we're going to substitute it into the standard, approximately standard normal distribution. And let's remind us the standard normal again. For the run test, we have z equals to r minus mu of r divided by sigma of r. So if you substitute all our value, the value we've gotten so far, if you substitute it into this formula here, we're going to have our number of r is 15, we have a mean subscript R to be equal to 22.76 from the previous slide, and we have a sigma R, which is standard deviation, to be 3.0363, and that's what we are going to do now. Substitute it into this formula. We have a Z equals to 15 minus 22.76 divided by 3.0363, and by the time we'll subtract this from this value, we're going to have a minus 7.76 over the denominator, which is a 3.0363. So finally, dividing this will give us negative result, and we're going to have a minus 2.307, which is approximately 2.3, that is into 2 significant figure. So we have our Z to be 2.3. So now this is the approximate standard number for this run test, and we have the value to be minus 2.3. Alright, so we've gotten the value for the statistical test, which is our step 3. Now the step 4 is to take decision. Now let's see what is here. We say step 4, decision rule. And what is our decision rule? And that is exactly what we're going to tell us here. But this test is two-tailed. Too few or too many runs could indicate randomly not generated, with alpha equal to 0.05 and alpha over 2 equals 0.025. The critical value are. Now the decision rule is to reject the hypothesis, the null hypothesis, if the observed value of the test statistic is greater than 1.96 or less than minus 9.6. Everything we've said here so far now, what are you trying to bring up from this point? What we're saying now is that the test is two-tailed. You should take note of this. That the test is two-tailed. We are running two-tailed test. Now, too few or too many runs could indicate randomly not generated. And what we mean by too many or too few? That is, if it is too few or it's too many, it means it's not going to fall in between the critical region. So it means if it falls out of the critical region, we will not have an option than to reject the null hypothesis. Again, we remind us that our level of significance remain 0.05, and by the time we divide this by 2, we're going to have 0.025, because we are dealing with two-tailed test, and that's why we divide it, which is 0.025. Now the critical value for standard number at 0.025 is plus minus 1.96. 1.96, that is minus 1.96 as the lower band plus 1.96 at the upper band. Now if the value of our run calculated run test, the value we just calculated now, do not fall in between minus 1.96 and plus 1.96, so this decision rule is to reject the null hypothesis. The decision rule is to reject the null hypothesis. Now, this will lead us to the next step, and that is step 5, which is conclusion. What are we going to conclude? We said the observed value of the test statistic, which is minus 2.3, is lower than the lower tail critical value, z equals to 1.96. We reject the null hypothesis and conclude that the observation in the sample were not generated randomly. So what are we saying here? The Z statistic, which is a run statistic, approximately standard normal statistic we calculated just now, the value is minus 2.3. And if you look at this minus 2.3, it's not in between 1.96 positive and 1.96 negative, which means the value is lower than this value here, is lower than minus 1.96, and as a result we're going to reject the null hypothesis. And when we reject the null hypothesis, the conclusion is that the observation in the sample were not randomly generated. The observation in the sample were not randomly generated. And that is how to use this large sample runs test. We should not forget that it is large sample run test because one of the n is greater than 20. If the two n's, the value of the two n is less than 20, then that is small sample run test. We have the video and we're going to show us that later. So this is how to calculate the run sample sample test. And thank you for your patience and for your understanding. If there is anything you need to ask, you can comment you can drop it in the comment section below. Please do not forget to subscribe to this channel. Thank you for watching.